4b is more about recurrence relations and the language we use when talking about them, and also about generating long recurrent sequences on a graphics calculator. You already know how to generate the beginning of a recurrence sequence using a scientific calculator or a graphics calculator. This is for generating long recurrent sequences. So the language. Now, if you remember from 4a, each term of a sequence is with a recurrence relation. It is generated by doing something to the previous term, like adding 3, multiplying by 4, dividing by 2, and so on. Now, what we need to get into our heads is that any particular term in the sequence is described in general by t little n, and we call that any term the nth term, not knowing what number we're talking about. It could be 7th term, it could be the 14th term, but the nth term is the position in the sequence of some random number n. The point being that the term before the nth term, tn, will be tn minus 1, and the term after the nth term will be term tn plus 1. You can see also on the screen there that the term before the tn minus 1 term will be t little n minus 2, and the term after tn plus 1 will be tn plus 2. So you'll get used to that, but that's just saying that the sequences go like tn, tn plus 1, tn plus 2, tn plus 3, tn plus 4, and of course you can go back, tn plus 5, tn plus 4, tn plus 3, tn plus 2, tn plus 1. That's just saying the same thing in my own writing rather than that of the textbook. So the way to write a recurrence relation using that language is to give the first term and then a comma, and then how to generate the next term. So t1 is obviously the first term, and in this case the number is 5. To get the next term, tn plus 1, we do 2 times whatever the previous term was, which in this case is 5, and then add 3. So 2 5s are 10 and 3 is 13. To get the next term, we find 2 times the term that we've got, which is 13. 2 times 13 is 26, plus 3 is 29, so that'll give us t3, and so on. That's what a recurrence relation looks like. It always says t1 equals something, and tn plus 1 is whatever you do to tn. That's why we need that language. All the recurrence relations that you'll be looking at should be written in that format. Okay, could you do it the other way around? So could you write a recurrence relation if you are given the first few terms? Now look at this one. Sequence is 400, 100, 25. So t1 is 400, t2 is 100, and t3 is 25. You're dividing each term by 4 to get the next one. So what you would write if you were asked to write that sequence as a recurrence relation is you'd write t1 equals 400, tn plus 1 equals tn divided by 4. Now, what if you want to generate hundreds of terms of a sequence, or find out the value of the 24th term of a recurrent sequence? Now, you could get your ordinary calculator out and just press enter, enter, enter 24 times, as long as you know how many enters you have pressed, which can often be wrong. Or you can get the graphics calculator to do it for you, and it will tell you the position of every term in the sequence. This is how you do it. First of all, you have to set your calculator into sequence mode. If you press mode, you will see that it's currently on function mode. And by the way, when you've finished working with a recurrence relations, you have to set it back to function mode, otherwise lots of things won't work. But for now, go down to function, then go across to SEQ sequence, and then you'll be in sequence mode. That's the first thing to do. By the way, I'm showing what you do on the TI-84CE, the pretty one. Further on in this presentation, there'll be a quick word about how to do it on the older calculator, which is pretty much the same. Now, To enter the initial value and the rule of a recurrence sequence, you do this. You press Y equals, which is on the top left of your calculator, having quit any other current dialog and cleared the screen. Now I'm going to show you how to put in this sequence: T1 equals 5, Tn plus 1 equals 2 times Tn plus 3. So for the sequence, we're going to be doubling the previous term and then adding 3. And we're starting at 5. Okay, looking at the displays below, they're slightly different. When I wrote this a couple of years ago, it looked like what's on the left, and now it looks like on the right. I'm not quite sure why there's much difference. Don't think it'll make any difference to you. Min equals 1, leave that as it is. It just means that we're starting with the first term as opposed to any other term. Now, on the next line, you put on the next line here, you are going to write in the rule of the sequence. Now, reading that, it says un equals 2 times un minus 1 plus 3. How do you put that into the calculator? Well, u is second function 7, so when you need a u, just go down to second function 7, and when you need an n, get that from the xt theta n button. I suggest you might want to pause this presentation while you do that, and then your next line, which on this display is u1, I don't quite know why, and on this display it is un min. That's where you put the 5, which is the first term. So once you've got that into the calculator, you can then see all the numbers in that sequence by second function table. N is the first column, and u of n is in the second column. So the first term was 5, the second term was 13, the third term was 29, and if you scroll down, you can find the 24th term without any difficulty. Don't worry about why the 0 term is producing an error, apart from the fact that it's doing that because you said n was 1. N of being 0 might not make any much sense, but in fact it does, as you will see later in the course on number sequences. Here it is on an ordinary graphics calculator, an old TI-84 graphics calculator. You still set mode to SEQ. You still do exactly the same thing, but your screen will look like that. un equals 2 times un minus 1 plus 3. un min, you just put a 5 in, and the sequence will look like that. As it says on the bottom of the screen, don't forget to set mode back to function when you finish with sequences. Okay, well that's the lesson for 4B. Questions look like this. I'm not going to go through them all with you, but just to make sure you know what's going on. Question 1, you're just making sure that you can use T5, T6, T7. So the symbol we use to represent the term before T7 will be T6. 2 terms after T9 will be to T11. That's question 1 kind of thing. Make sure you do all the questions. In question 2 there, you're given some of the terms in the sequence, 7, 9, 11, 13, so on. If Tn minus 1 equals 9, there's 9 here. That's if Tn minus 1 is 9, then the value of Tn will be the next term, because n comes after n minus 1, and that'll be 11. Okay, I'll do number C. If Tn is 15, write the value of n plus 2. Well, Tn is 15 there, so T of n plus 2 is 2 more terms after that, which is 19, and so on. Go back and finish all of this exercise when you finish my video. Question 3. Now it says without using your calculator, although I don't mind obviously if you check it, you can do it with the calculator. First 5 terms of the sequence. So let's just do the first one. This is fairly simple. T1 is 2. So each sequential term is 3 more than the previous one. So you are going to go 2, 5, 8, and so on. When you go down to these ones here, you're doing 2 things. You're doubling it and then subtracting 1 in this one here. Question 4. This time you're allowed to use the calculator. Again, whatever is easier, make sure you do most of them. And some exploring questions at the end of the exercise, questions 5 and 6. How many terms of the sequence formed from the recurrence relation below are positive? Well, if you put this sequence into your graphics calculator and just see which results are positive and count them up, and for this one, how many are negative. When you've done all that, I think you can confidently say that you can generalize the terms of a recurrence relation and write a recurrence relation and use the graphics calculator to generate long recurrence sequences. Finish off all of that exercise, and then the next lesson you'll be ready for 4C.